Yeah, hello everyone. Good afternoon. Am I visible and audible? Good afternoon, students. Yes. Okay. Okay. Yeah. Just give me a second. Okay. Yeah. So we are discussing with the periodic table, right? So last class only we have started this lesson and we have completed some of the introduction part and some informations related to periods and some informations related to groups. And coming to the good afternoon, Ramnagar students. Fine, good. So in the last class, we have ended up the class with discussing the blocks, right? So totally we have 4 blocks in the periodic table: S block, P block, D block, and F block. And S block and P block related informations I have discussed with you in the last class. Now in today's class, let's start with the D block. Okay. So who are these D block elements? So D block elements comprises of elements from group 3 to group 12, right? So they are also called as transition elements. So transition of properties takes place from S to T block. Thus D block elements are also called as transition elements. So these are the D block elements and it starts from group 3 to group 12. Okay. And it is placed in between the S block and T block. So why it is placed in between S block and P block? Because some of the properties of this D block elements, it will be mostly transition between S and P. Okay, will resemble S block as well as P block in some of its properties. So since it is exhibiting the properties of both S and P, or we can say it is transition between those two. Okay, so that's why they are called as transition elements. And D block also has general electronic configuration, which you can see it on the screen. It is n minus 1, D 1 to 10, and n is 0 to 2. Okay. So in case of scandium, the configuration would be 3D 1, 4s 2. In case of titanium, it is 3D 2, 4s 2. Like that, it goes on till zinc. And when you're coming to this 4D element, which is yttrium, so it starts from 4D1, 5s2. Okay. When moving on to the next element, zirconium, it is 4D2, 5s2. Like that, it goes on. Okay. But the last group, that is group number 12, zinc, cadmium, and mercury, these 3 elements does not show most of the properties of the transition elements. Okay. So zinc, cadmium, and mercury, these elements are not called as transition elements, but they are D block elements. Okay. So why it is not called as transition element? You see here the electronic configuration, it is n minus 1 D. Suppose in case of zinc, the configuration would be 3D10 and 4s2. Okay, this is the configuration. And you see the d orbital is completely filled. So we have 5 d orbitals. Each orbital takes 2 electrons. So already 10 is present. D orbital is fully filled. Okay, so the electron cannot come out from the d orbital. So the reaction will not take place with the d electron. So it will not resemble the transition elements properties. Transition means there should be some movement. Okay, movement of electron takes place. So here no movement of d electron takes place in case of zinc, cadmium, and mercury. So that's why they are not regarded as transition elements, but they are d block elements. Since the last electron is entering into the d orbital, it is called as d block, but it is not called as transition element. Okay. Now all the metals and mostly form colored ions. Okay, D block elements, all of them are metals mostly. So they all form colored ions. They exhibit variable valency. They exhibit paramagnetism and they are used as a catalyst. Okay, so all the D block elements form colored ions. They are able to produce a color when they are put inside the solution. and they exhibit variable valency, means they can exhibit a variable oxidation state. Suppose if I am taking iron, if I am taking this iron can exist in 2 plus state as well as 3 plus state. Okay, so like this, more they are exhibiting different variable valency, and they exhibit paramagnetism. So what is paramagnetism? The unpaired electron containing species are called as paramagnetism. So all the d block elements are mostly paramagnetic in nature, and if a compound is if a substance is paramagnetic in nature, that substance will get attracted towards the magnetic field. So d block elements are paramagnetic in nature, so they will go and get attracted towards the magnetic field. And also it is used as a catalyst. So what is the role of the catalyst? To speed up the reaction. To alter the rate of the reaction is the job of the catalyst. So in all of the organic chemistry part, we have discussed hydrocarbons and the general organic chemistry lessons. In all those lessons, you might have noticed that we have used, in most of the cases, we have used palladium, nickel, and platinum, right? All these elements are D block elements. They are used as a catalyst, which speed up the reaction. Okay. So these are the general informations about the D block. So any doubt from the D block part? Shall we move on to the last block, that is F block? Then we Ramnagar students, you have any doubt from this? No. Okay. So now moving on to the F block. In F block, if you see, most of all the elements are metals. All are mostly metals. And the electronic configuration exhibited by F block element is N-2 F1 to 14, N-1 D0 to 1, and NS2. Okay, so we have only two F series. One is 4F and the other one is 5F. If the electron is getting filled in the 4F orbital, then we call those elements as lanthanoids. And if the electrons are getting added into the 5F orbital, then we call those elements as actinoids. Okay, you see here for lanthanoid, here n value will be 6. So 6 is 2 and 6 minus 1 is 5, right? So 5D0 to 1 and 6 minus 2 is 4. 4 of 1 to 14. So this would be the configuration for lanthanoids. Whereas in case of actinoids, it is 5 of 14, 5 of 1 to 14, 6D0 to 1 and 7 is 2. Okay. For lanthanoid, 4 of is getting filled and for actinoids, 5 of is getting filled. That's all. And coming to this actinoids, the study of the chemistry is very complicated. Why? Because most of the actinoid elements are radioactive in nature. So because of that radioactivity property, the elements cannot be stabilized. They are not stable. They are almost unstable in nature. If a compound or if an element is unstable, then we cannot able to study the chemistry of that particular element, right? So that's why we cannot study, and it is very complicated due to its radioactive nature. And if you see the elements of actinoids, elements after uranium, they are called as trans-uranium elements. So where is the uranium? So here we have thorium, and this is protactinium, and here is the uranium. And after uranium, we have neptunium, plutonium, etc. So from this neptunium till this lawrencium, those elements are called as trans-uranium elements. Okay, so that's all about the F block also. You just need to keep in mind the electronic configuration of F block, which is very important. And the two series are called as lanthanoids and actinoids. And the elements which is present after uranium are called as trans-uranium elements. And the chemistry is very difficult. Study of chemistry is very difficult for actinoids because they are radioactive. That's all. So these are the points you are going to keep in mind for F block. So is it clear? Any doubt from F block? So that's all about the informations related to blocks, that is S block, P block, D block and F block. Okay. Now I will move on to the classification of metals, non-metals and metalloids. So they are also there in the periodic table only, right? So first let's start with the metals. Okay. So 78% of all known elements that is the left side of the periodic table, they mostly consist of metals. Okay, metals means, will it be solid or liquid or gas? What is the nature of the metal? Can you tell me the nature of the metal? Will it be a solid thing or liquid or gas? What is the nature, physical state of a metal? Very good. Yeah, it is solid. So they are generally solid, but there is an exception. There is an exception. The exception is mercury. Hg is mercury, the D block element which I was talking before few minutes. Okay, and gallium and cesium. Gallium is a P block and cesium is an F block. Sorry, S block. So these two elements, they have very low melting point. So mostly metals will have high melting point. Okay, but these three elements, they are exception. Mercury, gallium, and cesium, they have a low melting point. So I'll show you the picture. You can see here, mercury is a liquid metal. Okay, it is a liquid metal, so it gets melt so easily. And gallium also we have studied, the properties of gallium and P block elements. When I was discussing the group 13 elements, I have told you about this low melting nature of gallium. Okay, it's having very low melting point, and this is the gallium metal. And some of the general properties of the metals are, they have high melting point and boiling point. They are the good conductors of heat and electricity, and they are ductile and malleable. So most of the metals, if you see, they conduct heat and electricity. For example, iron you can take, copper you can take. So they are used for electricity purpose, and they can conduct the heat, right? They are the good conductors, and they are also ductile and malleable. So what is meant by ductility? Ductility is the ability to drawn into thin wires. So what we can do, we can take a metal, okay, we can drawn into a thin wire and we can roll it. So most of the metals, they have this ductility property. And what is malleability? Malleability means you can hammer a metal, okay? You can hammer a metal and you can take the shape of the metal which you want. You can make the shape which you want, okay? So they are also, metals are also malleable in nature. We can take the shape which we want according to our availability, okay? So that is the ductility and malleability property of these metals. So these are some of the general characteristics of metals, which will be discussed in class 12 also. So there is one lesson called D and F block elements for you in class 12. So there we will discuss this again in detail. Okay. There also we'll study this. But now you just learn the general properties of all the metals. Okay. Now coming to the non-metals information. So most of the non-metals, they are present at the top right side of the periodic table. The top right hand side of the periodic table consists of non-metals. So can you name some of the elements that is present at the top right hand side of the periodic table? Top right hand side means it is P block, right? So can you guys name one or two non-metals that is present at the top right-hand side of the periodic table? So who are the elements present at the top right-hand side of the periodic table? Helium, we have oxygen, we have nitrogen, we have fluorine, argon, etc., neon, etc., right? So they are the elements which are present at the top right-hand side of the periodic table. So these non-metals generally, they are solid, okay, or gases, but with low melting point or boiling point. And also there is an exception, that is boron and carbon. They don't have low melting or boiling point, okay. And some of the properties of the non-metals are, they are the poor conductors of heat and electricity. Just the opposite of metals. They will not, non-metals will not conduct heat. Will oxygen conduct heat? No, it will not conduct, right? So it is a non-metal. So they won't conduct heat and they won't conduct electricity also. And they are neither ductile nor malleable. So we cannot because it is not a solid, right? Mostly it won't be in the solid form. So we cannot draw into a thin wire, or we cannot hammer and we can take the shape which we want. So that those properties are not applicable for non-metals. So they are neither ductile nor malleable. Okay. So these are the properties of non-metals. And coming to the last one, that is metalloids. So metalloids are otherwise called as semi-metals. Metalloids are otherwise called as semi-metals. Okay. So most of the metalloids you can find in the P block. So generally they are found immersed in P block, and the elements which show the properties of both metals and non-metals are called as semi-metals or metalloids. Okay. Is this clear for all? If you're having any doubt, just let me know. If it is clear, just give me a thumbs up or type yes in the chat box. These are some of the general introductions, okay, related to the elements. Shall we move on to the next slide, students? Yes. JNV Ramnagar, Bharat and Medak. Am I audible? No, ma'am. It's for what? You don't have any doubt, or you're having any? Shall I move on to the next slide? Okay. Okay, fine. Yeah. Yeah. Thank you so much, students. Yeah. So here you can see the color differentiation for all the elements, right? So the blue, kind of orange, and the light pink and dark pink, those elements are metals. So means all the S block will fall under this category, and all the D block will fall under this category, and all the F block will fall under this category, and this will not fall. These two elements, okay, these two elements representation is this. So they are metals. And the non-metallic elements are green and pink. Means this boron, carbon, nitrogen, oxygen, no, they are non-metals, and all the 18th group elements, they are non-metals. And the elements which you can see in the orange color here, from silicon, germanium, arsenic, antimony, tellurium, polonium, astatine. So these elements are metalloids. These are the metalloids. So in the periodic table, 75% of the elements are made up of metals only. Very few non-metal and very, very few metalloids. Got it? So now we will move on to one question. Yeah. In terms of period and group, where would you locate the element with atomic number 117? So in which period and in which group you will place the element whose atomic number is 117? Can anyone try for this? In which period number and group number I want? Try for this and let me know the answer in the chat box. It's very easy. It's very easy. 7th period and very good. Yeah, it is 7th period and 17th group, because the electronic configuration is this, and period number is 7 and group number is also 7. Very good. It belongs to halogen family. Highest principal quantum number is 7. So if we are having an element with atomic number 119, where will you place that element with 119 atomic number? Ma'am, we don't have 119 element and all in the periodic table, so it is out of question. Will you say like that? Or if you guys are discovering that element with the atomic number 119, where will you place that element? In which block, in which period, and in which group you will place that element 119? It's very easy. 118, first group, 8th period. Very good. First group, 8th period. 120, Second group, 8th period. It goes on. Very good. Good. Really great. And let me just summarize from the first that we have discussed in the last class also. I have discussed the modern periodic table with you in the last class. And there were 7 periods and 18 groups. Valence electronic configuration. They were similar for some elements, so they exhibited similar chemical properties. And there were 4 blocks, S, P, D, and F. And the elements which lie at the borderline between metal and non-metal are called as metalloids or semi-metals. Okay, so this is a summary. Now let us move on to the second half of this lesson. So which is the trends in physical properties of elements. So we will study both the properties, physical property as well as chemical property. So first let us complete this physical property and its trend, and then we will study about the chemical properties and its trend. Okay. So now moving on to the physical property, we are going to study 4 physical property. One is atomic and ionic radii. Second is ionization enthalpy, electron gain enthalpy, electronegativity. So these are the 4 physical properties which we are going to study in this lesson, which are very, very important and very basic to the whole chemistry. Okay, you will get questions from this physical properties part. So concentrate more on it. Now let us start from the atomic and ionic radii property. Atomic and ionic radii. So I'll start this with a question to you. Why exact measurement of atomic radii is not possible? What is actually a radius? So in maths you might have studied, no? So there will be a circle, there will be a center point, and distance between the center point and the edge is called as radius. So now for chemistry, let us take this as an atom. This is atom A. Now the measuring the radius for this atom A is very, very difficult. The exact measurement of the radius of an atom is very, very difficult, and it is not possible also. Why? Why the exact measurement of atomic radii is not possible? There are 2 reasons. The first reason is the size of the atom is very, very small. Size of the atom is very, very small. So this is the atom. So this is the nucleus. Neutrons and protons are there inside the nucleus, and red color and black color balls you can see. And these are the electrons. Electrons are revolving in its orbits, okay, around the nucleus. And this is an atom. The size of this atom is very, very small, and that's why we are not able to find out the radius of an isolated atom. Okay. Now the second reason is, so this is an atom again. In terms of electron density, it is shown to you. And this is the nucleus. Center part is the nucleus, which you can see. And the blue color dots, they represent the electron cloud. Okay. So this electron cloud is not providing a definite boundary to us. You just see here, it is just spreaded over around the nucleus, right? So we don't have definite boundary. Just see, if I draw a line here, some of the electron density, it is also present outside this line. Okay, so there is no definite boundary for an atom, and the size of the atom is very, very small. Because of these 2 reasons, we cannot able to measure the atomic radii of an atom. Got it? So now to measure the atomic radii, what I have to do? Measure the atomic radii or to ionic radii, what I have to do? In what way I can measure? I can measure. Shall I move on to the next slide, students? Did you guys noted it down? Is this clear? Yes. Okay. Yeah. So the atomic and ionic radii can be calculated by indirect methods. So what are those indirect methods? We can calculate the radius of an atom from its covalent radii, and from its metallic radii, and from its van der Waals radii. Okay. So let's start from the first, that is covalent radii. So covalent radii means I have to take a covalently bonded atom, right? So for example, I will take chlorine. So chlorine molecule is taken. Okay, chlorine is a molecule, and one chlorine is bonded with another chlorine by covalent bond. Covalent bond means there will be the mutual sharing of electron between the two atoms. Okay, mutual sharing of electron leads to the covalent bond. And now there is a covalent bond between the two chlorine. And if you see the distance between the nucleus of those two chlorine, this is the nucleus of first chlorine, this is the nucleus of the second chlorine. And if we take the distance between these two chlorine, it is 198 picometer. Okay. Now, to find out the atomic radii or covalent radii, I have to take the half of the internuclear distance between the two covalently bonded atoms. That will give me the covalent radius. So what I have to do, this 198 picometer is nothing but the internuclear distance. Internuclear distance is denoted by the letter D. This internuclear distance here we are having, no, this is denoted by the letter D. And half of the internuclear distance, that is D by 2. D by 2 will give us the covalent radius R. What I have to do, D value is 198. And if I divide this by 2, I will get R, and R would be 99 picometer. 99 picometer is the covalent radius of chlorine molecule. Got it? Any doubt from this? Very easy. If in the question if they are asking you to find out the covalent radius of a molecule, just take the number and divide it by 2. Okay? Or if they are confusing with you with the units, like picometer, in that units, if they are confusing you, you just do it accordingly. Okay? Just very easy. Shall we move on to the next thing? Half of the internuclear distance between the two covalently bonded atoms is called as covalent radius. Yes. Thank you, students. Yeah. Some more information. Yeah. Definition for bond length. Okay. I told you, right? The distance between the two nucleus of a covalently bonded atom is called as internuclear distance, and it is denoted by the letter D. It is denoted by the letter D, and that D is called as the bond length. That D is also called as bond length, and that bond length or that internuclear distance D divided by 2 gives us the covalent radii. Okay, so basically this internuclear distance and bond length, they are equal. So this is the point we are getting from this. Now let me go with the metallic radii, the second indirect method to calculate the radius, that is metallic radii. So the definition is the half of the internuclear distance separating the metal cores in the metallic crystal. So we have to take a metal. I'll take copper metal for you. Yeah, this is the copper metal. Now you see the two copper atoms. It is not overlapped with each other, like in case of chlorine. So in case of chlorine, we had this overlapping, right? So this type of overlapping is not possible in case of metal. Just they will touch each other. An atom will just touch each other, and there are nucleus for two atoms. And if we connect the two nucleus, we will get one distance value, right? So that is 256 picometer for copper, and that is the D value, internuclear distance we can say, and that D by 2 will give us the metallic radius R. So D by 2 is equal to 128. That's all. Okay, same as that of the previous case. You have to just take the half of the given number. Okay, their overlapping occurs, and here no such overlapping occurs. So now you tell me, now you compare covalent radii and metallic radii and tell me which value will be more. Covalent radius will be more or metallic radii will be more? Which radii will be more when we compare these two? Take the overlapping concept and try to answer for this. Covalent radii will be more or metallic radii will be more? Just say any one. Very good. It is metallic radii because in covalent we have overlapping. But in case of metallic, we don't have such overlapping. So the internuclear distance here, it will be very less, and here it will be little bit higher than the first case. Okay. Now let's move on to the third radii, that is van der Waals radii. So mostly van der Waals radii is observed in noble gases. When noble gases, they mostly exist as monoatomic gases, right? They mostly exist as monoatomic, like helium, He, neon, argon, krypton, xenon, like that. Only one atom will be there. So in case of nitrogen, we have N2, oxygen O2, right? So these are diatomic in nature, but all the noble gases are monoatomic in nature. Okay. Now the atomic radius is calculated using van der Waals radius. So when the two monoatomic noble gases, when they are solidified, two atoms of that noble gas will try to come closer with each other. Just see it in the picture. So they will try to come closer with each other. They will not form the bond, but there will be some force of interaction between the two atoms when they come closer to each other. Okay. So that force of interaction is called as van der Waals interaction. It is one of the very weakest interaction which we can say. Okay. Very weakest interaction because there is no formation of bond between the two atoms. For noble gases, outermost shell is already completely filled, so there will not be any formation of bond, but there will be some force of attraction. Okay, and here you can see the distance between the two nucleus of the noble gases is represented by D again, and D by 2 will give us R. Got it? Now you tell me. Now you compare all the three radius and tell me which radius will be higher, which will be more. This is van der Waals radii and this is covalent radius. Which radius will be more when you compare van der Waals and covalent? Very easy, right? Van der Waals radius is obviously greater than the covalent radius. When you compare all the three, van der Waals will have the highest value, then comes metallic, then comes covalent. Okay. So because of this particular higher value of this noble gases, higher radius value of this noble gases have abnormally large atomic radius compared to its period member. Okay, I'll tell you while discussing the trend of this atomic radius in the next slide. Okay, so mostly noble gases will have the large atomic radius. So this point alone you just keep in mind now. And while discussing the trend, I will explain you this in the detailed manner. Got it? Shall we move on to the trend of atomic radii across the period and on moving down the group? So far what I have discussed is clear to all of you, or if you're having any doubt, you can let me know in the chat box. Yes? Okay. Good. First of all, let's go with the trend of atomic radii across the period. Across the period means moving from left to right. Okay. I'll show you the values of the second period and third period element. Second period elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. You see here, neon is not given. Fluorine is 17th group. 18th group elements are not given here. You see, because that will have exceptionally value compared to this fluorine. And if you see the trend for the second period and third period, the lithium atomic radius is 152 picometer and it is gradually decreasing, and fluorine is having 64. So from left to right, that is across the period, atomic radius decreases. Okay, and for third period elements also you can see, starting from 186, it is ending up with 99. Across the period, size decreases. Why it decreases? What is the reason? Outer electrons are in the same valence shell across the period. That's why they are getting decreased. Suppose if this is lithium, and if this is beryllium, and if this is boron, all these lithium, beryllium, boron, all these elements belongs to the second period, right? Second period means there will be the nucleus for all the atom, And this is the first shell and this is the second shell. So this is the first shell, second shell. So this is the first shell and second. So second shell is the valence shell for all the elements which are there in the second period element. Okay. Now coming to the electron distribution. Atomic number of lithium is 3 and for beryllium it is 4 and for boron it is 5. So what is atomic number? It is the number of electrons or the number of protons in the neutral atom. Now I will talk about the electron. If the atomic number of lithium is 3, then it has 3 electrons. So the first 2 electron goes to the first shell and the third electron goes to the second shell. In case of beryllium, first 2 goes to first shell and remaining 2 more we are having they enter into the second shell. In case of boron, 2 in shell number 1 and 3 in shell number 2. So when you see here, for lithium, in the outermost shell, we have only 1 electron. It is getting attracted towards the nucleus. And for beryllium, we have 2 electrons in the valence shell, in the outermost shell. So there will be the force of attraction for the 2 electron towards this nucleus. And when you come to boron, boron has 3 electron in its valence shell. So all 3 will get attracted towards the nucleus. So what is happening? Electrons are getting added into the same shell, okay, due to which the force of attraction between the nucleus and the electron increases. If the force of attraction increases, contraction occurs, right? So that's why the atomic radius decreases from left to right. Is this clear for all? If it is clear, just give me a response. If it is not clear, type it in the chat box. I will explain you again because these are very, very important concepts which you need to know for the whole inorganic part of chemistry. Is it fine? Why there is no response from my class 11 students? Is it okay? Or shall I explain again? Students, are you there? Yes. Once again. Okay. I'll explain you with a good and neat diagram so that you will understand, I think. So this is the lithium atom. And this is the beryllium atom. And this is the boron atom. Atomic number for lithium is 3, beryllium 4, boron 5. Just for an example, I have took these 3 elements, okay? So this trend is followed for the whole elements, which is there in the corresponding period. And each atom has nucleus inside it, right? Now, all these elements are second period element. So they will have 2 shell and second shell will be the outermost shell. So this is shell number 1 and this is shell number 2. For all the 3 atoms, it is this the case. Now, since lithium is having the atomic number 3, it has 3 electrons. So always remember, in the first shell, we can put only 2 electrons. In the first shell, we can put only 2 electrons. So from this 3, 2 electron enters into the first shell and the third electron enters into the second shell. Okay. Now electrons are negatively charged and the nucleus is positively charged. Opposite charges will get attracted towards each other, right? So the outermost electron is getting attracted towards this nucleus. Got it? Now coming to beryllium, in the first shell, 2 electron. In the second shell also we have 2 electron because atomic number is 4. We have 4 electrons. And those 2 electrons which are there in the outermost shell, they are getting attracted towards the nucleus. And in case of boron, in the same manner, 2 in the first shell and 3 electron in the outermost shell. So all the 3 valence electron or the outermost electron is getting attracted. Now, The attraction is more in case of boron. So what happens? Contraction occurs, right? So lithium is there, okay, and after the 2 electrons, so contraction occurs, and if I add one more electron, again the attraction occurs there. So still some contraction is happening there. So because of this, the radius is decreasing. Lithium, beryllium, boron, carbon, nitrogen, like that, it goes on decreasing. Is this clear now? Attraction between the nucleus and the outermost electron increases. That's all. We can tell it like effective nuclear charge increases. So because of this, you can see it in the graph. Lithium to fluorine, you see atomic radius is decreasing from lithium to fluorine because the effective nuclear charge increases, and so the atomic radius also decreases. The Ramnagar students, is this okay? Yeah. Now coming to the trend of atomic radius, no issues, okay? We will go with the trend of atomic radius across the group. So let me take two groups. The first is group number 1 and the second column is group number 17. Okay. So if you see the trend, the values are getting increased. So on moving down the group, size of the element increases. Atomic size increases. Got it? So across the period, it decreases, and on moving down the group, it increases. That's all. Why it increases? Why the atomic, you see here, see it in the graph. For group 1, atomic radius is increasing from lithium to cesium. And for fluorine till iodine also, it is getting increased. Why it is getting increased? Because the number of shells is getting increased. Because of this, atomic radius is also getting increased. So for in case of fluorine, chlorine, bromine and iodine, fluorine is the second period element. Fluorine is a second period element. Excuse me, sorry. And chlorine is a third period element. Bromine is fourth period and iodine is fifth period. Okay. Now fluorine, for fluorine, the outermost shell is 2. So this is a nucleus, shell number 1, shell number 2. And for chlorine, this is the nucleus, shell number 1, 2, 3. And for bromine, 1, 2, 3, 4. And for iodine, 1, 2, 3, 4, 5. So what is happening here? Number of shells is getting increased. Okay. So the electron, the outermost electron and the nucleus, if you see, the distance between the outermost electron and the nucleus is increasing. If the distance increases, attraction decreases. Okay. So the size increases on moving down the group. Due to the increase in N is nothing but the number of the shell. Due to increase in the number of the shell, electrons are also filled in inner shells which shield the valence electron. Don't get confused with this. On moving down the group, number of shell increases, so size increases. That's all. Got it? Is it okay? General trend is across the period decreases, moving down the group increases. That's all. Yeah. So now we have studied the trend for this atomic radii. And before this, we have studied 3 radius: covalent, metallic, and van der Waals. From those 3 indirect methods, we have calculated the radius of a corresponding atom present in that molecule, or in a metal crystal lattice, or in case of noble gases, we can say. Now, we have one more radii, which is called as ionic radii. Now, how to estimate the ionic radii? How to calculate the ionic radii? It is the distance between the nucleus and the outermost electron of the ion. How many ions we have? 2 ions. One is cation and the other one is anion, right? So we have to take the distance between the nucleus and the outermost electron in that ion, and that will give us the radius of that cation or anion. Okay, distance between the ions in the ionic lattice is sum of the size of cation and anion. So this is the ionic lattice. So we have cation and anion here. The small sized purple color balls, they represent the cation, and the big size green atoms, they represent the anion. Okay, the sum of the size of the cation and anion in the ionic lattice and the distance between them will give us the radius of the ion. So this is the radius of the cation, which is denoted by R plus, because here is the nucleus. No, so this is the nucleus and this is the outermost electron. So that is R plus, and this is R minus. This is the nucleus and this is the outermost electron. That is R minus. And if you add those two, if you take the sum of cation and anion, that will give you the distance between those two. Okay. So this is called as the ionic radii. Okay. I'll show you. So let me take a neutral atom. This is the neutral atom. And if I remove one electron from this neutral atom, I will get a cation, right? So for example, if I am taking this neutral atom as sodium, and if I remove one electron from sodium, I will get sodium plus, and that is the cation. And you see the size there. Neutral atom is bigger in size and cation is very smaller in size. And in the same way for anion, I'm taking a neutral atom and this neutral atom is chlorine. Okay. And if chlorine gains one electron, it will be converted to Cl minus, which is an anion. Now, when we compare the neutral atom and anion size, anionic size is bigger compared to the neutral atom. Okay. So now if I want to take all the three, that is cation and the neutral atom and the anion, anions will have the highest size value, then comes neutral atom, then comes the cation. So this is the order which you have to follow if the same species are asked in the question. Okay. So the cationic size is getting lesser than the neutral atom because of the effective nuclear charge. Effective nuclear charge inside the cation increases. And the anionic size is getting far bigger compared to the neutral atom because there is an increase in the repulsion between the electron. So that is the reason. Now you see here, this is the neutral atom, this is the anion of it, this is the cation of it. So suppose, we can take iodine. Okay, iodine, I minus and I plus. I minus will have the highest value. Got it? So ionic radius, they exhibit the same trend across the periodic table as atomic radius. So what was the trend observed for atomic radius? Across the period, atomic radius decreases, and on moving down the group, atomic radius increases. The same trend is followed for ionic radius also. Across the period decreases, moving down the group increases. Got it? Fine. I think it's already 3:55. You have to go for the next class. So I'll stop here. In the next class, I will discuss some more informations related to this ionic radius, and then we can move on to the second physical property, that is ionization energy. Okay. So far you concentrate on the periods, groups and blocks related informations, metal, semi-metal, and metalloids and non-metals. And then in the physical property, I have discussed the first physical property, atomic size. And under that atomic size, 4 different radius are there: covalent, metallic, van der Waals, and ionic. So till this, you study and try to solve questions on this. In the next class, we can continue this lesson with the ionization energy after completing this atomic size related information. Okay. If you're having any doubt, you can tell me now. If you're not having any doubt, we can meet up in the next class. Okay. Okay, then. Thank you, students. Bye-bye.